This is the story of Stevenson 218, a star so massive that if you placed it where our Sun sits today, its surface would swallow Mercury, Venus, Earth, Mars, Jupiter, and reach past Saturn's orbit into the outer solar system. Light takes 9 hours to circle this monster once, compared to the 14.5 seconds needed to loop around our Sun. Astronomers discovered this cosmic leviathan hiding in plain sight, 20,000 light-years away in the constellation Scutum, and when they calculated its dimensions, the numbers broke every expectation about how large a star could actually grow. The measurements placed Stevenson 218 at roughly 2,150 times the radius of the Sun, which translates to a volume 10 billion times greater than the star that lights our world. Understanding what makes this star possible, why it exists at all, and what fate awaits it, reveals some of the most extreme processes in the universe. American astronomer Charles Bruce Stephenson spent years examining infrared survey data from the northern Milky Way when he noticed something peculiar in the constellation Scutum during 1990. Buried deep in photographs taken with the Burrell-Schmidt telescope at the Warner and Swasey Observatory, he identified 10 faint objects heavily reddened by intervening dust, several showing the distinct signatures of M-type supergiants. What he'd found wasn't a single star but an entire cluster, later designated Stevenson 2, packed with some of the most massive and luminous objects in the galaxy. At the time, Stevenson estimated the cluster lay about 98,000 light-years away, an enormous distance that would make its members incredibly bright to be visible at all. Later observations revised this figure dramatically downward to roughly 18 to 20,000 light-years, placing the cluster at the intersection where the long bar of our galaxy meets the inner edge of the Scutum-Centaurus arm, one of the Milky Way's 2 major spiral arms. The cluster designation RSGC2, short for Red Supergiant Cluster 2, tells you exactly what made Stephenson's discovery extraordinary. Astronomers had found similar collections before, but never one quite like this. The core of Stevenson 2 contains 26 confirmed red supergiant members, the largest known population of these dying giants anywhere in our galaxy or beyond. Red supergiants represent stars in their final chapters, bloated and cool, burning through the last nuclear fuel available before catastrophic collapse. Finding them clustered together in such numbers suggests an environment where star formation occurred in an intense burst, creating dozens of massive stars that have now all reached their terminal phases at roughly the same time. The brightest member of this cluster received the simple designation 1 in the first analysis of cluster properties from 2007, when researchers led by Davies examined the region in detail. Nobody considered it a proper cluster member initially because its position seemed off, its brightness exceeded expectations, and its motion through space differed from neighbouring stars. Some team members suggested it might be a foreground giant, closer to us and merely appearing aligned with the cluster by chance. Others noted that the star displayed significant infrared excess, likely from extreme mass loss episodes, which could indicate it was a red hypergiant rather than an ordinary red supergiant. The debate about membership continues today because radial velocity measurements show the star moving at 89 km per second, while the cluster average sits at 109 km per second, a difference large enough to raise questions but not definitive enough to rule out association completely. Later surveys assigned this mysterious object the number 18 and placed it in a subgroup called Stevenson 2SW, a loose collection of stars lying southwest of the main cluster. This led to the designation Stevenson 2-18, though you'll also see it called ST2-18, RSGC2-01, Stevenson 2-DFK-1, or simply D1 in various papers. The multiple names reflect different teams working on the same region, each adopting their own numbering schemes, which created considerable confusion in the literature. Some papers refer to D1 when discussing mass loss rates, others use ST2-18 when calculating luminosity, and still others stick with the RSGC2-01 designation from earlier catalogues. All these names point to the same object, a star that has captured attention because its size pushes against theoretical limits for how big a red supergiant can grow. Measuring the distance to Stevenson 2-18 presented challenges because the cluster itself sits hidden behind enormous amounts of galactic dust. The constellation Scutum lies close to the galactic plane, where dust concentrations are thickest, completely blocking visible light from these stars. Early infrared surveys could penetrate this obscuration enough to detect the brightest members, but determining precise distances required other methods. Teams used kinematic distance calculations, which compare the star's radial velocity to models of galactic rotation, arriving at values between 5.5 and 6 kiloparsecs, translating to roughly 18,000 to 20,000 light-years. The uncertainty in these measurements exceeds 50%, meaning the actual distance could differ substantially from published values, which in turn affects every derived property like luminosity and radius. A study from 2013 by Verheyen and colleagues used average radial velocities from multiple cluster members to derive a kinematic distance of approximately 6 kiloparsecs. They noted that Stephenson 218's radial velocity fell below the cluster mean, which led them to classify it as a field-red supergiant unassociated with Stephenson 2 itself. This interpretation suggests the star might lie closer or farther than the cluster, occupying a different region of space that just happens to align with our view of RSGC2. Other researchers disagreed, pointing out that expanding stellar envelopes can offset radial velocity measurements, and that the star's high mass loss rate could create thick circumstellar material that affects how we measure its motion. The question remains unresolved, with some papers treating Stephenson 218 as a cluster member, and others considering it an isolated giant that happens to share the same line of sight. The importance of establishing membership goes beyond simple classification, because it determines which distance we should use for calculations. If Stephenson 218 belongs to the cluster at 6 kiloparsecs, we can apply the cluster distance with reasonable confidence. If it's a foreground or background object, we need independent distance measurements, which are extremely difficult for single red supergiants. The star's properties, like luminosity and radius, scale directly with distance squared, so getting the distance wrong by even 20% throws off the final numbers significantly. Teams have calculated luminosities ranging from 90,000 solar luminosities based on 12 and 25 micrometer flux densities, assuming 5.5 kiloparsec distance, up to 630,000 solar luminosities using spectral energy distribution integration at 5.8 kiloparsecs. That's a factor of 7 spread in luminosity estimates, all for the same star. What makes Stephenson 218 particularly interesting from an observational standpoint is that we can't see it with ordinary telescopes. The surrounding dust concentration is so thick that visible light simply doesn't make it through. Amateur astronomers searching for this object in scutum will find nothing, because the wavelengths our eyes detect get completely absorbed and scattered by intervening material. Only infrared observations reveal the star's presence, and even then, the heavy reddening affects measurements. The star's spectral energy distribution appears peculiar compared to standard models, with fluxes that don't fit expected reddening laws. This suggests either unusual circumstellar material around the star itself, or variable extinction along the line of sight through the interstellar medium, both of which complicate efforts to determine its true nature. The 2012 study using the Australia Telescope Compact Array and the DUSTY model produced the famous estimate of 440,000 solar luminosities and an effective temperature of 3,200 Kelvin. These values, plugged into the Stefan-Boltzmann equation, relating luminosity to temperature and radius, yielded a radius of 2,150 solar radii, or roughly 10 astronomical units. That measurement put Stephenson 218 firmly at the top of the size rankings, larger than any other confirmed stellar radius at that time. The figure shocked astronomers because theoretical models of red supergiant evolution predicted maximum radii around 1,500 solar radii, making this star 30 to 40% bigger than physics suggested should be possible. Either the measurements contained systematic errors, which remains possible given the uncertain distance and high extinction, or red supergiants can grow larger than standard stellar evolution models allow. Observations from water mesas detected around Stephenson 218 support the interpretation that this star is experiencing extreme mass loss. Mesas are regions where molecules like water or silicon monoxide emit coherent microwave radiation, acting like natural lasers. They form in the cool, dense shells of material streaming away from red supergiant surfaces, and their presence indicates vigorous stellar winds. The maser emissions from Stephenson 218 and another cluster member designated D2 showed the highest mass loss rates among all studied stars in RSGC2, suggesting both objects are shedding material at prodigious rates. Only the most luminous stars in the cluster produce detectable masers, which makes sense because higher luminosity means stronger radiation pressure to drive winds. The maser observations also revealed expanding shells of gas at different velocities, indicating multiple episodes of mass ejection rather than steady outflow. Silicate emission features at 10 and 18 micrometers provide additional evidence for circumstellar dust around Stephenson 218. These features arise from silicon-oxygen bonds in small dust grains that condense in the cooling stellar wind. The strength of these emission lines tells astronomers about dust composition and temperature, which in turn constrains mass loss history. Strong silicate features suggest substantial dust production, which requires heavy mass loss to supply enough material for grain formation. The combination of water masers, silicate emission, and high infrared excess paints a picture of a star surrounded by thick shells of gas and dust, actively shedding its outer layers in the prelude to some future transformation. Grasping the actual size of Stephenson 2-18 requires moving beyond simple numbers into physical comparisons that make the scale tangible. The star's radius of 2,150 solar radii means you could fit over 10 billion suns inside its volume, which sounds impressive until you realise that volume scales as radius cubed, making even small increases in radius translate to enormous jumps in volume. Earth has a radius of about 6,371 kilometres, and our Sun measures roughly 696,340 kilometres across. Stephenson 218 dwarfs both to the point where they become essentially invisible specks against its immensity. If you could somehow place Earth and Sun side by side inside this monster, they would be like comparing a grain of sand to a basketball. Except the scale difference is even more extreme. Astronomers often describe stellar sizes by comparing them to our solar system, because it provides a familiar framework most people understand. Our solar system spans from the Sun's surface out to the orbit of Neptune at roughly 30 astronomical units, though the heliosphere extends farther, and objects like Pluto and scattered disk bodies reach well beyond that distance. Stephenson 218's radius of 10 astronomical units means its surface would sit between the orbits of Jupiter and Saturn if you replaced our Sun with this giant. Mercury, orbiting at 0.4 astronomical units, would find itself deep inside the star's photosphere. Venus at 0.7 astronomical units, likewise engulfed. Earth at 1 astronomical unit, buried. Mars at 1.5 astronomical units, consumed. The asteroid belt between 2 and 3 astronomical units, vaporized. Jupiter's orbit at 5.2 astronomical units, well inside. Saturn orbits at about 9.5 astronomical units, placing it right at the edge or just inside the star's outer layers, depending on exactly how you measure the stellar radius. The concept of a stellar surface becomes fuzzy for red supergiants because their outer atmospheres are so diffuse that density drops gradually rather than ending at a sharp boundary. Where precisely do you say the star stops and space begins, when the atmosphere just fades into the surrounding interstellar medium? Astronomers typically define the radius as the point where optical depth reaches a specific value, meaning where the gas becomes opaque enough to block light from deeper layers. This convention works well for normal stars but becomes problematic for extreme objects like Stephenson 218, where the atmosphere extends far beyond the photosphere in complex shells and envelopes. Different wavelengths of light see different optical depths at different radii, so measurements in visible light might give one radius, while infrared observations suggest another. The quoted radius of 2,150 solar radii represents an average derived from bolometric luminosity and effective temperature, providing a general sense of scale even if the exact boundary remains ambiguous. Light's journey around Stephenson 2-18 takes approximately 9 hours compared to 14.5 seconds for our Sun, which illustrates the enormous difference in circumference. Light travels at 300,000 kilometers per second, covering tremendous distances in short times, yet even at that speed, it needs 9 hours to loop this star once. That's longer than a standard workday, longer than most people sleep, long enough to fly from New York to Tokyo. During those 9 hours, light from the Sun could travel to Jupiter and back multiple times, or reach all the way to Saturn. The fact that one star's surface can be so large that light requires most of a workday to circle it once demonstrates just how far removed these objects are from normal stellar scales. Temperature provides another axis of comparison that reveals how different Stephenson 2-18 is from our Sun. The Sun's surface temperature sits around 5,770 Kelvin, hot enough to emit most strongly in visible wavelengths, which is why our eyes evolved to see in that range. Stephenson 2-18's effective temperature of 3,200 Kelvin makes it much cooler, placing it firmly in the red portion of the spectrum. At this temperature, the star glows deep red, emitting most of its energy in infrared wavelengths invisible to human eyes. The cooler temperature is a direct consequence of the enormous radius, because luminosity depends on both temperature and surface area, and Stephenson 2-18 achieves its high luminosity through sheer size rather than heat. The relationship between radius, temperature and luminosity follows from the Stefan-Boltzmann law, which states that luminosity equals 4 pi times radius squared times the Stefan-Boltzmann constant times temperature to the 4th power. Temperature appears to the 4th power, making it a strong factor, but radius is squared and red supergiants can increase their radius dramatically. When a star expands to 2,000 times solar radius, that factor of 2,000 gets squared to become 4 million, which more than compensates for the reduction in temperature from 5,770 Kelvin to 3,200 Kelvin. The 4th power of temperature ratio is about 0.12, but the radius ratio squared is 4 million, so the final luminosity ends up hundreds of thousands of times solar despite the much cooler surface. This extreme luminosity means that Stephenson 2-18 radiates as much energy in a single day as our Sun produces in nearly 2 years, and the star maintains this output continuously. The energy comes from nuclear fusion reactions in the core where helium burns into carbon and oxygen, releasing vast amounts of energy that eventually makes its way to the surface and escapes as light. The star must burn through enormous quantities of helium every second to sustain this luminosity, which is precisely why red supergiants have such short lifespans. They consume fuel at rates that would drain their reserves in mere millions of years, a blink compared to the Sun's 10 billion year lifetime. Energy transport from core to surface in red supergiants occurs mainly through convection rather than radiation. The interior of these stars contains huge convective cells where hot gas rises from deep layers, cools as it nears the surface, then sinks back down to be reheated. These convective motions can be violent, creating surface features and driving pulsations that cause the star to vary in brightness over time. Most red supergiants show some degree of visual variability, with periods ranging from months to years, and amplitudes that can reach several magnitudes. Stephenson 2-18 likely varies as well, though monitoring it is difficult given the heavy obscuration and the need for infrared observations. The variability arises from convective overturn, acoustic waves propagating through the atmosphere, and the star's inherent instability as it struggles to maintain equilibrium between gravity, pulling inward, and radiation pressure pushing outward. The surface gravity on Stephenson 2-18 is incredibly weak compared to normal stars. Gravity at the surface scales as mass divided by radius squared, and while red supergiants have substantial masses, their radii are so enormous that the denominator dominates. A typical red supergiant might have surface gravity 1,000th of the Sun's, and Stephenson 2-18's extreme radius pushes that even lower. This weak gravity makes it easy for material to escape, which is why these stars experience such intense mass loss. The escape velocity from the surface is less than 100 km per second, compared to 618 km per second for the Sun. Radiation pressure from the star's intense luminosity can accelerate gas and dust grains beyond escape velocity with relative ease, driving powerful stellar winds that carry away significant fractions of the star's mass over its lifetime. Watching Stephenson 2-18 from a hypothetical planet would be an awe-inspiring and terrifying experience. The star would dominate the entire sky, appearing not as a point of light, but as a vast glowing dome filling your field of view. The deep red colour would bathe everything in crimson light, creating an alien landscape unlike anything we experience under our Sun. The heat would be intense, far too hot for liquid water or habitable conditions, with surface temperatures on any planet within a few astronomical units, reaching thousands of degrees. The stellar disk would show visible structure, with darker and brighter patches corresponding to convective cells and pulsation modes. Mass loss events would appear as shells of glowing gas, expanding outward from the surface, sometimes detaching to form discrete clouds. The experience would be both beautiful and menacing, a reminder that you're watching a dying giant in its last throes before destruction. Stars like Stevenson 218 don't form the way our Sun did, because the initial conditions required to create such massive objects are fundamentally different. Star formation begins in molecular clouds, vast regions of cold gas and dust that span hundreds of light years and contain masses equivalent to hundreds of thousands or even millions of suns. These clouds represent the coldest, densest parts of the interstellar medium, with temperatures hovering around 10 Kelvin above absolute zero and densities of 10,000 to 1 million particles per cubic centimetre, which is still incredibly sparse by terrestrial standards but dense for space. The clouds consist mainly of molecular hydrogen, with trace amounts of helium, carbon monoxide, water, and more complex organic molecules that radio telescopes can detect. Molecular clouds are not static but show active dynamics driven by turbulence, magnetic fields, and gravitational instabilities. Turbulence creates chaotic motions at all scales, with gas streaming in random directions at velocities of several kilometers per second. This turbulence supports the cloud against gravitational collapse on large scales because the internal kinetic energy counteracts gravity's pull. However, turbulence also creates local overdensities where compression from colliding flows concentrates material into denser clumps. When one of these clumps reaches sufficient density, its self-gravity begins to dominate over turbulent support and collapse ensues. The transition from supported cloud to collapsing core marks the start of star formation. The collapse process proceeds hierarchically, with the initial cloud fragmenting into progressively smaller pieces as it contracts. Large-scale collapse creates filamentary structures where material streams along magnetic field lines, accumulating in dense cores where filaments intersect. Observations from infrared space telescopes like Spitzer and Herschel have revealed these filaments in exquisite detail, showing networks of dark lanes threaded through glowing clouds. The filaments are not uniform but display a characteristic thickness of around 0.1 parsec, regardless of the cloud's overall mass, suggesting some universal physical process sets this scale. Stars form within the densest parts of filaments, where gravity has gathered enough material to overcome internal pressure and magnetic support. For massive stars like the progenitor of Stephenson 218, formation requires unusually dense and massive clumps within the molecular cloud. Low-mass stars like our Sun form from cores containing just a solar mass or two of material, which collapse relatively slowly over hundreds of thousands of years. Massive star formation involves cores with tens or hundreds of solar masses that collapse much faster, compressing under their own gravity in just tens of thousands of years. This rapid collapse presents challenges because the infalling material releases gravitational potential energy as heat, warming the core and creating outward pressure that could halt further accretion. Massive protostars must somehow continue accreting, despite their own radiation trying to push material away. The solution involves accretion disks and jets similar to those seen around low-mass protostars but scaled up enormously. Material doesn't fall straight into the forming star but instead spirals inward through a rotating disk of gas and dust. Angular momentum conservation ensures that collapsing material retains some rotation from the original cloud's turbulent motions, forcing it into a disk configuration. The disk acts as a buffer, allowing material to gradually spiral inward while radiating away energy through collisions and friction. Some material gets ejected perpendicular to the disk in powerful bipolar jets, driven by magnetic fields threading the disk and star. These jets punch through the surrounding envelope, clearing paths that allow radiation to escape and reducing the pressure on infalling material. Observations of massive protostars show complex structures including disks, envelopes, outflows, and ionization fronts, where ultraviolet radiation from the central star heats surrounding gas. The Orion Nebula cluster provides excellent examples of massive star formation in progress, with several young O and B stars still embedded in their natal clouds. Infrared observations penetrate the dust to reveal the protostars, while millimeter-wave observations trace molecular line emission from the surrounding gas, mapping velocities and densities. These studies confirm that massive stars form through disk accretion, rather than mergers between lower mass stars, though competitive accretion where protostars in crowded regions grow by capturing material from neighbours likely plays a role in determining the final mass distribution. The initial mass function describes how many stars form at each mass, with low-mass stars vastly outnumbering high-mass ones. For every star with 15 or 20 solar masses, thousands of solar mass stars form, making massive stars rare products of star formation. This rarity reflects the difficulty of assembling so much mass in one location before radiation pressure from the forming star disperses the remaining cloud. Only the densest, most massive clumps in the most active star-forming regions can produce stars massive enough to eventually become red supergiants like Stephenson 218. The progenitor likely started with an initial mass between 15 and 25 solar masses based on stellar evolution models that predict which stars reach the red supergiant phase before core collapse. Young massive stars spend their first few million years on the main sequence, burning hydrogen into helium in their cores through the CNO cycle, rather than the proton-proton chain that powers the Sun. The CNO cycle dominates at temperatures above 20 million Kelvin, which massive stars reach easily. This cycle is much more temperature sensitive than the proton-proton chain, scaling as temperature to the 16th power or higher, which makes massive stars incredibly luminous right from the start. A 15 solar mass star on the main sequence shines at around 30,000 solar luminosities, already more than enough to be visible across the galaxy. The intense luminosity creates strong radiation pressure that drives stellar winds even during the main sequence phase, with mass loss rates around 10 to the -6 solar masses per year. Main sequence lifetimes for massive stars are surprisingly short because their cores burn through hydrogen at such high rates. The Sun will spend about 10 billion years on the main sequence, fusing hydrogen for the vast majority of its existence. A 15 solar mass star exhausts its core hydrogen in just 10 to 15 million years, about 1,000th as long. This rapid evolution means that massive stars are always young compared to their lower mass cousins. The Stevenson 2 cluster has an estimated age of 14 to 20 million years, which means its red supergiant members have already finished their main sequence phase and progressed into later evolutionary stages. The fact that so many red supergiants appear together indicates a burst of star formation created dozens of massive stars within a short time window, all of which are now dying together. After hydrogen exhaustion, the star's core contracts and heats up while a shell of hydrogen burning forms around the inert helium core. This structural change causes the outer envelope to expand dramatically as the star transitions off the main sequence toward the red supergiant region of the Hertzsprung-Russell diagram. The expansion occurs over thousands of years, fast by astronomical standards but slow enough that we rarely catch stars in the act. During this phase, the star's radius increases by factors of hundreds, while its surface temperature drops from 30,000 Kelvin or more down to 3,000 or 4,000 Kelvin, transforming a blue supergiant into a red one. The total luminosity may increase somewhat, but not as dramatically as the radius, because the cooler temperature partially offsets the larger surface area. Red supergiants represent the dying days of massive stars, a brief but spectacular phase lasting around 1 million years before the final collapse. Stars in this stage have exhausted hydrogen in their cores and are burning helium into carbon and oxygen, with additional shell burning of hydrogen in layers surrounding the core. The internal structure resembles an onion, with concentric shells of different compositions and temperatures, each undergoing nuclear fusion at different rates. This complex structure is inherently unstable because each shell responds to changes in adjacent layers with different timescales, creating oscillations and variations that manifest as surface pulsations. The photosphere of a red supergiant extends to enormous distances because the density drops so gradually that light can escape from deep layers. Unlike main sequence stars where the photosphere occupies a relatively thin shell, red supergiants have photospheres that span a significant fraction of the stellar radius. This extended photosphere means different wavelengths of light emerge from different depths, with ultraviolet and visible light coming from shallower layers and infrared from deeper, hotter regions. Spectroscopic observations reveal this stratification through the presence of molecular absorption bands that form only in the coolest outer layers, where molecules can exist without being dissociated by heat or radiation. Temperature stratification in the atmosphere creates complex radiative transfer as light from hot inner regions interacts with overlying cooler gas. Some wavelengths get absorbed and re-emitted multiple times before escaping, while others pass through relatively unimpeded. This leads to the formation of spectral features including absorption lines from neutral and ionized atoms, molecular bands from titanium oxide and other molecules, and maester emission from water and silicon monoxide in the circumstellar envelope. The spectrum of Stephenson 2-18 shows characteristics typical of late M-type supergiants, with strong titanium oxide bands indicating a surface temperature around 3000 Kelvin and spectral type, around M6, which is unusually cool even for red supergiants. Convection dominates energy transport throughout most of the red supergiant envelope because the opacity is high enough that radiative diffusion becomes inefficient. Enormous convective cells develop, with diameters comparable to the stellar radius itself. These cells rise from deep in the star, carrying energy to the surface, where it radiates away, then cool and sink back down. The timescale for convective overturn can be months to years, which drives the observed variability in red supergiant brightness. As hot cells reach the surface, the luminosity increases, then drops as cooler material takes their place. The pulsations are semi-regular rather than strictly periodic, because the convective patterns themselves are chaotic and variable. Surface features on red supergiants likely resemble extremely large versions of sunspots, with bright areas corresponding to rising hot plumes and dark areas to sinking cool regions. High-resolution interferometric observations of nearby red supergiants like Betelgeuse have detected such features directly, showing mottled surfaces with temperature contrasts of hundreds of degrees. For Stephenson 2-18, the enormous distance and heavy obscuration make direct imaging impossible with current technology, but the physical processes should be similar. The surface is probably covered with a few giant convective cells, creating bright spots the size of Jupiter's orbit, with darker regions where cooler material descends. Pulsations in red supergiants can reach amplitudes of a magnitude or more, meaning the star varies by factors of 2 to 3 in brightness. These variations don't follow simple patterns because they result from multiple oscillation modes superimposed on the irregular convective cycles. Some pulsations are radial, with the entire star expanding and contracting in sync, while others are non-radial with different parts of the surface moving in opposite directions. Radial pulsations can create shock waves that propagate through the atmosphere, heating the gas and driving mass loss. Non-radial modes create complex surface patterns that contribute to the overall variability without necessarily producing coherent oscillations. Mass loss becomes critical during the red supergiant phase because the combination of low surface gravity, high luminosity and pulsations creates perfect conditions for stellar winds. Radiation pressure on dust grains that condense in the cool outer atmosphere accelerates them outward, and these grains drag gas along through collisions, creating a wind that flows away from the star at velocities of 10 to 30 km per second. The mass loss rate depends on luminosity, with the most luminous red supergiants losing mass fastest. Stephenson 2018 has an estimated mass loss rate around 1.35 times 10 to the -5 solar masses per year, which ranks among the highest known for any red supergiant. This mass loss rate means the star sheds the equivalent of an entire sun's worth of material every 74,000 years, which sounds slow until you realise the red supergiant phase only lasts 1 million years. Over that time, Stephenson 2-18 could lose 10 solar masses or more, fundamentally altering its structure and evolution. The expelled material forms an expanding circumstellar envelope that surrounds the star in nested shells, each corresponding to a different epoch of mass loss. When we observe Stephenson 2-18 in infrared wavelengths, we're seeing not just the star but this entire complex of circumstellar gas and dust that scatters and absorbs light before it reaches us. The maester emission detected around Stephenson 2-18 arises from water molecules in these circumstellar shells, where physical conditions create population inversions that amplify microwave radiation. Water masers require specific combinations of temperature, density and radiation, field strength to operate, typically found in shells a few hundred to a few thousand stellar radii from the surface. The maester emission can be used to map the velocity structure of the outflow, revealing whether material flows uniformly in all directions or preferentially along certain axes. Observations of Stevenson 218's mesas show complex kinematics consistent with a clumpy, structured wind rather than a smooth spherical outflow. Understanding mass loss mechanisms in red supergiants remains an active research area because current physics can't explain the observed rates from first principles. Radiation pressure on dust grains clearly plays a role, but the details of how grains form, grow, and couple to the gas are not well understood. Pulsations probably help by creating density enhancements where grains can condense more easily, and by launching shockwaves that accelerate material. Convective motions might also contribute by creating localized outflows from hotspots on the surface. Some researchers propose that magnetic fields play a role, though evidence for strong fields in red supergiants is limited. The complexity of these processes makes it difficult to predict mass loss rates accurately, which in turn creates uncertainties in stellar evolution models. The chemical composition of red supergiant atmospheres shows enrichment in elements produced by nuclear burning in the core. Convection can dredge material from burned layers up to the surface, changing the observed abundances of carbon, nitrogen, and oxygen. First dredge-up occurs when stars first ascend the red giant branch, bringing helium-burning products to the surface. Later episodes can occur during the red supergiant phase, though the extent of mixing depends on details of the convective zones and how deeply they penetrate. Surface abundance patterns provide clues about the star's mass, age, and evolutionary history because different burning stages produce characteristic abundance signatures. Observations of Stephenson 218's spectrum could potentially reveal these abundance patterns, but the heavy interstellar extinction and complicated circumstellar environment make detailed spectroscopy challenging. The presence of strong molecular absorption bands indicates the surface is cool enough for molecules to survive, and titanium oxide bands suggest an oxygen-rich chemistry rather than carbon-rich. This is consistent with a star that has experienced helium burning but not yet undergone the thermal pulses that would enrich the surface in carbon and transform it into a carbon star. The overall picture is of a star still burning helium in its core, probably with some carbon and oxygen already present from partial burning, but not yet having progressed to later stages like carbon burning. Stevenson 2-18 doesn't exist in isolation, but resides in or near one of the most remarkable stellar clusters in our galaxy. The Stevenson 2 cluster contains at least 26 confirmed red supergiant members, with recent surveys identifying upwards of 80 potential members spread over a larger region than typical clusters. This enormous population of dying massive stars makes Stephenson 2 unique, as no other known cluster in or out of the Milky Way contains so many red supergiants. The cluster's location near the intersection of the Long Bar and the Scutum Centaurus arm places it in a region of active star formation where massive molecular clouds have created bursts of stellar birth over the past few tens of millions of years. The cluster age estimates of 14 to 20 million years imply that all its massive stars should have finished their main sequence evolution and entered later phases. Stars with initial masses around 12 to 16 solar masses spend roughly that amount of time on the main sequence before transitioning to supergiants, so the cluster age matches the expected lifetime for its members. The fact that we see them all as red supergiants rather than a mix of evolutionary states suggests they formed in a relatively short burst, probably over just a few million years. This synchronization creates the spectacular population we observe today, with dozens of dying giants clustered together. Population synthesis models struggle to explain clusters this rich in red supergiants, because they require specific combinations of initial mass function, star formation rate, and cluster age that are statistically unlikely. A cluster needs to form dozens of stars in the right mass range to eventually produce this many red supergiants, which requires a particularly massive and dense molecular cloud, undergoing vigorous star formation. The Stephenson 2 region appears to have met these conditions, possibly triggered by collisions between spiral arm gas and bar material, or by shock compression from nearby supernova remnants. Understanding what makes this cluster special could provide insights into the conditions required for massive star formation more generally. The spatial distribution of red supergiants in Stephenson 2 is not compact, but spread over several arc minutes on the sky, corresponding to tens of parsecs at the cluster's distance. This extended structure suggests the cluster is more like an OB association than a tight open cluster, with member stars dispersed through a larger region of active star formation. Some researchers propose that Stevenson 2 blends into its surroundings, forming part of a much larger stellar complex containing hundreds of massive stars at various evolutionary stages. The red supergiants we identify as cluster members might represent just the tip of the iceberg, with many more massive stars present, but not yet evolved to the red supergiant phase or already past it. Individual cluster members show a range of properties despite their similar ages and evolutionary states. Luminosities vary from less than 100,000 to more than 500,000 solar luminosities, radii from about 700 to over 2,000 solar radii, and mass loss rates spanning orders of magnitude. This diversity reflects differences in initial mass, rotation, and possibly metallicity, all of which affect stellar evolution and the red supergiant phase. More massive progenitors become more luminous red supergiants, but may also evolve through this phase faster, transitioning blueward or exploding before lower mass stars. Rotation can affect mixing and mass loss, potentially extending or shortening the red supergiant lifetime. Several particularly notable members deserve mention alongside Stevenson 2-18 for their extreme properties. Stevenson 2 DFK2, also known as D2, shows high mass loss rates comparable to D1 and displays strong maester emission. Stephenson 2 DFK49 is a peculiar object that may be a post-red supergiant star evolving blueward, showing characteristics intermediate between red and yellow hypergiants. Stephenson 2 DFK52 was recently revealed to have an enormous outflow extending up to 50,000 astronomical units, unprecedented even for extreme red supergiants, suggesting unique mass loss mechanisms. Each of these stars provides different perspectives on the final evolution of massive stars and the diversity of outcomes possible. The cluster's heavy obscuration has prevented detailed studies until relatively recently, when infrared capabilities improved enough to penetrate the dust. Early observations could detect the brightest members, but struggled with fainter objects and could not obtain high-quality spectra. Modern infrared spectrographs on large telescopes can now acquire spectra of individual stars, measuring radial velocities, determining spectral types, and constraining stellar parameters. These observations have revolutionized our understanding of the cluster, revealing its true extent and complexity. Radial velocity measurements provide crucial information about cluster membership and internal dynamics. Most confirmed members show radial velocities clustered around 109 km per second, consistent with the cluster participating in galactic rotation at its distance. Stars with significantly different velocities are likely foreground or background objects superimposed on the cluster by chance. The velocity dispersion within the cluster appears modest, suggesting the system is gravitationally bound or was at formation, though whether it will remain bound over timescales of billions of years is unclear given the limited mass in red supergiants compared to the original stellar population. The future evolution of Stephenson 2 will be dramatic as its red supergiants begin exploding as supernovae over the next few million years. With potentially dozens of massive stars nearing core collapse, the cluster will experience a supernova rate far higher than the galactic average. These explosions will inject enormous amounts of energy into the surrounding interstellar medium, creating bubbles of hot shocked gas that expand and merge. The combined effect could disperse remaining molecular cloud material, terminating further star formation, and perhaps triggering collapse in adjacent clouds through compression. Supernova remnants from the first explosions might still be expanding when later stars go off, leading to complex interactions. Mass loss dominates the final evolution of stars like Stevenson 2-18 because it determines whether they remain red supergiants until core collapse or evolve back across the Hertzsprung-Russell diagram to become blue supergiants or Wolf-Rayet stars. Theoretical models show that stars losing mass above a certain threshold can strip away their hydrogen envelopes, exposing deeper layers and increasing surface temperature. The critical mass loss rate depends on the star's luminosity and initial mass, with more luminous stars requiring higher rates to strip the envelope. Stevenson 2018's mass loss rate of roughly 1.35 times 10 to the -5 solar masses per year places it near or above this threshold. The physical mechanism driving such intense mass loss involves a combination of factors working together. Radiation pressure on dust grains forms the primary engine, with photons from the star scattering off tiny particles of silicates, iron, and other condensates. Each scattering event transfers momentum to the grain, accelerating it outward. When grains reach sufficient velocity, they collide with gas atoms and molecules, dragging them along through friction. This grain-gas coupling allows the wind to carry away material that would otherwise remain bound to the star. The efficiency of this process depends critically on the grain formation rate, because if too few grains condense, radiation pressure cannot generate sufficient thrust. Grain formation occurs in the cool outer atmosphere where temperatures drop below condensation thresholds for various materials. Silicates form at around 1000 Kelvin, iron at similar temperatures, and carbon-based grains at slightly higher temperatures for carbon stars. The grains start as tiny clusters of a few atoms that gradually grow by accreting more material from the gas phase. Turbulence and density fluctuations create regions where growth can occur more efficiently, leading to a population of grains with varying sizes and compositions. Observations of scattered light around red supergiants show evidence for these grains, with polarization patterns indicating aligned non-spherical particles. Pulsations enhance mass loss by creating density waves that propagate through the atmosphere, creating high-density shells where grain formation is enhanced. When the star pulsates radially, the entire photosphere moves outward and inward periodically. During expansion phases, the atmosphere cools and density increases, favoring grain condensation. The newly formed grains get swept up by radiation pressure and accelerated outward before the next pulsation cycle. This pulsation-driven mass loss can be significantly more efficient than steady-state winds, because it creates episodic bursts of grain formation rather than requiring continuous nucleation. Shock waves generated by pulsations add another layer of complexity to the mass loss process. When the photosphere expands rapidly during a pulsation, it can create compression waves that steepen into shocks as they propagate outward. These shocks heat the gas temporarily, creating bright spectral features and possibly triggering additional chemistry. Behind the shock front, the gas cools rapidly, potentially creating favourable conditions for molecule formation and grain growth. The passage of multiple shocks through the circumstellar envelope produces layered structures visible in molecular line emission. The circumstellar envelope around Stevenson 218 contains multiple components, including a present-day wind close to the star, detached shells from past mass loss episodes, and a more extended halo of previously ejected material. Each component has distinct physical properties including density, temperature, velocity, and chemical composition. The present wind flows at about 10 to 27 km per second based on Massa observations, which is typical for red supergiant winds. Detached shells show evidence for higher velocities, suggesting past episodes of enhanced mass loss, possibly during pulsation outbursts or other instabilities. Water Massa emission provides a powerful diagnostic of the innermost circumstellar environment, where the wind first forms and accelerates. Water molecules require specific conditions to produce Massa action, typically found at radii of a few hundred to 1,000 stellar radii, where the temperature is around 1000. Kelvin and densities are high enough for collisional pumping. The Massa emission can be spatially resolved using very long baseline interferometry, revealing clumpy structures and non-spherical geometries in some cases. For Stevenson 2-18, the Massa observations indicate complex kinematics with multiple velocity components, suggesting either bipolar outflows or a clumpy wind structure. Silicon monoxide masers trace slightly different regions than water masers, typically forming closer to the star where temperatures are higher. The combination of both types provides information about the density and temperature structure throughout the circumstellar envelope. Observations of other red supergiants show that Massa emission correlates with high luminosity and high mass loss rates, which makes sense because both masses and strong winds require intense radiation fields to drive the chemistry and dynamics. The fact that Stevenson 218 displays both water and silicon monoxide masers confirms its status as an extreme object. The chemical composition of the circumstellar material reflects what the star is ejecting, which includes not just hydrogen and helium, but also the products of nuclear burning like carbon, nitrogen, and oxygen. These elements get incorporated into molecules and dust grains in the cooling wind, creating the silicate features observed in infrared spectra. The 10 and 18 micrometer silicate emission bands are particularly strong in Stephenson 2-18, indicating abundant dust production. The shape and strength of these features can constrain dust composition and grain size distributions, though degeneracies exist because multiple combinations of parameters can produce similar spectra. Mass loss during the red supergiant phase significantly affects the final fate of the star because it determines how much mass remains when the core collapses. A star that begins with 20 solar masses but loses half its envelope through winds will have very different supernova properties than one retaining its full mass. The amount of hydrogen in the envelope affects the supernova light curve, with hydrogen-rich explosions producing type 2p supernovae that show a characteristic plateau in brightness as the ejecta recombine. Stars that lose their entire hydrogen envelope before exploding produce type Ib or EC supernovae with different light curves and spectra, where the Stephenson 2-18 will explode with its hydrogen envelope intact or strip it away before core collapse depends on how mass loss evolves over the next few 100,000 years. If the current high mass loss rate continues, the star could lose most of its envelope and transition to a hotter spectral type. If mass loss declines or the star's core collapses before envelope stripping completes, it will likely explode as a hydrogen-rich supernova. Theoretical models give different predictions depending on assumptions about mass loss prescriptions, which remain uncertain precisely because we don't understand the physics completely. Every red supergiant is living on borrowed time, counting down to the moment when its core exhausts the last fuel capable of generating energy through fusion. For Stephenson 2-18, that moment lies somewhere in the next few 100,000 years, possibly much sooner if the star is more evolved than appearances suggest. The exact timeline depends on the current core composition, mass loss history and internal mixing, all of which affect how quickly the star burns through its remaining fuel. Once iron begins accumulating in the core, the clock speeds up dramatically because iron cannot undergo fusion to release energy, and the end comes within just a few years. The sequence of burning stages after helium exhaustion follows a predictable pattern dictated by nuclear physics and thermodynamics. When helium burning creates enough carbon and oxygen in the core that fusion can no longer maintain the pressure needed to support the overlying layers, the core contracts again and heats up. At temperatures around 600 million Kelvin, carbon ignites through the triple alpha process modified for heavier nuclei, fusing carbon atoms into neon, sodium and magnesium. This releases energy that halts the contraction temporarily, but carbon burning proceeds rapidly, exhausting the core carbon in just a few thousand years. Each subsequent burning stage occurs faster than the previous one because the core grows hotter and denser with each contraction, accelerating reaction rates. Neon burning follows carbon burning when temperatures reach 1.2 billion Kelvin, converting neon into oxygen and magnesium through photodisintegration processes. Oxygen burning starts at about 1.8 billion Kelvin, producing silicon and sulfur. Finally, silicon burning begins at temperatures exceeding 3 billion Kelvin, creating iron peak elements like iron, nickel, and cobalt. The silicon burning phase lasts only days to weeks, making it the briefest stage of stellar evolution. The structure of the star during these late burning stages resembles an onion with concentric shells of different compositions, each undergoing fusion at different rates. The innermost core contains the products of the most recent burning stage, surrounded by shells of lighter elements left over from earlier phases. For a star like Stephenson 2-18, you might find an iron core surrounded by silicon, oxygen, neon, carbon, helium, and finally hydrogen shells moving outward through the star. Each shell has its own temperature, density, and energy generation rate, creating a delicate balance that maintains the star's structure. The iron core grows as silicon burning converts overlying material into iron peak elements that fall onto the core's surface. Iron represents the end of the line for fusion because it has the highest binding energy per nucleon of any element, making it the most stable nucleus. Fusing iron into heavier elements requires energy input rather than releasing it, so iron accumulation shuts down energy production in the core. With no energy source to maintain pressure against gravity, the core becomes supported solely by electron degeneracy pressure, the same quantum mechanical effect that supports white dwarfs. Electron degeneracy pressure arises from the Pauli exclusion principle, which states that no two electrons can occupy the same quantum state. When matter compresses to high densities, electrons fill all available low-energy states, and further compression requires promoting electrons to higher energy levels. This creates a pressure that depends on density but not temperature, making it distinct from thermal pressure. Degeneracy pressure can support stellar cores against gravity, up to the Chandrasekhar limit of about 1.4 solar masses. Beyond this mass, electron degeneracy pressure becomes insufficient and the core is doomed to collapse. The exact Chandrasekhar mass depends on composition, with iron cores having limits around 1.3 to 1.4 solar masses. Stellar evolution models predict that massive stars develop iron cores near this limit through silicon burning, which means the core teeters on the edge of instability as it grows. Two processes accelerate the final collapse once the core reaches critical mass. First, photodisintegration breaks down iron nuclei into helium and free neutrons when core temperatures exceed 10 billion Kelvin, absorbing energy and reducing pressure. Second, electron capture by protons in nuclei removes electrons from the gas, reducing degeneracy pressure. These processes trigger runaway collapse because both reduce pressure support, allowing gravity to compress the core further, which increases temperature and density, accelerating photodisintegration and electron capture in a positive feedback loop. The collapse proceeds catastrophically, with the core shrinking from the size of Earth to the size of a city in less than a second. Velocities reach 23% of light speed as material falls inward, converting gravitational potential energy into kinetic energy at an astronomical rate. When the core density reaches nuclear density around 400 trillion grams per cubic centimeter, neutron degeneracy pressure abruptly halts the collapse. At this density, neutrons are packed as tightly as particles in an atomic nucleus, and the strong nuclear force creates a repulsive pressure that stops further compression. The sudden halt sends a shock wave propagating outward through the infalling material, reversing its motion and beginning the supernova explosion. The shock wave initially carries enormous energy, enough to unbind the entire star, but as it passes through dense inner layers, it loses energy to photodisintegration and neutrino losses. Neutrinos play a critical role in core collapse supernovae because they carry away more than 99% of the energy released during collapse. The collapsing core becomes so dense and hot that neutrinos of all flavors are produced in vast numbers through various weak interaction processes. Most of these neutrinos escape the star without interacting, but a tiny fraction deposits energy in the material behind the stalled shock, potentially reviving it and driving the explosion. This neutrino heating mechanism remains uncertain despite decades of research, because the details of neutrino transport and energy deposition are extremely complex. Three-dimensional hydrodynamic simulations of core collapse supernovae show that convection and turbulence in the region behind the shock, called the gain region, may play crucial roles in explosion. Neutrinos heating this region create bubbles of hot gas that rise buoyantly, generating turbulent motions that can prolong the time the shock spends in the gain region and increase total energy deposition. Standing accretion shock instabilities can also develop, creating large-scale oscillations that enhance neutrino heating. These multidimensional effects are difficult to capture in one-dimensional models, which is why understanding the explosion mechanism requires state-of-the-art supercomputer simulations. For Stevenson 218, the supernova explosion will be spectacular, possibly reaching peak brightness comparable to an entire galaxy of stars. The explosion will synthesize new elements through explosive nucleosynthesis as the shockwave passes through the stellar layers, creating elements from silicon to nickel that don't form in normal stellar burning. Radioactive nickel-56 produced in the explosion will power the light curve as it decays to cobalt and then iron, creating the characteristic glow that can last for months. The total energy released will approach 10 to the 51 ergs, with most escaping as neutrinos but enough remaining in kinetic energy to accelerate several solar masses of material to thousands of kilometers per second. The visual display when Stephenson 218 explodes will be extraordinary even from 20,000 light-years away. The supernova may reach apparent magnitude around 0 to -5, making it visible to the naked eye and possibly the brightest star in Earth's night sky for weeks to months. Astronomers across the world will rush to observe it across all wavelengths, from radio to gamma rays, gathering data that will provide insights into core collapse physics, nucleosynthesis, and supernova progenitors. The neutrino burst will arrive hours before the optical brightening, giving advance warning and triggering worldwide alerts for neutrino detectors to prepare for the event. After the supernova fades, a compact remnant will remain at the location where Stevenson 2-18 once shone. The nature of this remnant, whether neutron star or black hole, depends on the mass of the collapsing core and the details of the explosion mechanism. Standard stellar evolution models predict that stars with initial masses between 8 and 20 solar masses leave neutron star remnants, while more massive stars produce black holes. However, mass loss during evolution complicates this picture because it reduces the total mass and affects the final core mass. Neutron stars represent one possible outcome: stellar corpses composed almost entirely of neutrons packed to nuclear density. These objects measure only about 20 kilometers in diameter, but contain 1.4 to 2.1 solar masses, making them the densest objects in the universe aside from black holes. The matter in a neutron star exists in exotic states not found anywhere else, with a crust of neutron-rich nuclei above an interior of neutron superfluid and possibly quark matter in the deepest regions. The intense gravity creates space-time curvature so extreme that general relativistic effects become important, with time dilation and gravitational redshift reaching measurable levels. Newly formed neutron stars rotate rapidly, because conservation of angular momentum amplifies any initial rotation as the core collapses from Earth-size to city-size dimensions. Typical rotation periods at birth are 10 to 100 milliseconds, meaning the neutron star spins 10 to 100 times per second. If the neutron star has a strong magnetic field, which most do, this rapid rotation creates a pulsar, a cosmic lighthouse that sweeps beams of electromagnetic radiation across space. When Earth lies in the path of these beams, we detect regular pulses at radio, optical, X-ray or gamma-ray wavelengths, allowing detailed study of neutron star properties. The fastest spinning known neutron star rotates 716 times per second, approaching the theoretical maximum set by the requirement that centrifugal forces at the surface don't exceed the gravitational binding. Most pulsars slow down over time as they lose rotational energy to electromagnetic radiation and particle winds, with spin-down rates providing information about magnetic field strength and braking mechanisms. Young pulsars are typically found near supernova remnants, directly linking them to core collapse events. The Crab Nebula contains perhaps the most famous example, with a pulsar spinning 30 times per second surrounded by the expanding debris from the 1054 supernova. Black holes form when the collapsing core exceeds the maximum mass for neutron star stability, currently estimated around 2 to 3 solar masses, though the exact value remains uncertain. Once matter compresses beyond this limit, no known force can halt further collapse, and the object shrinks inside its event horizon to become a black hole. The event horizon radius depends on mass through the Schwarzschild radius formula, giving roughly 3 kilometers per solar mass. A 3 solar mass black hole would have an event horizon about 9 kilometers across, smaller than a neutron star of similar mass. Nothing can escape from inside the event horizon because the escape velocity exceeds the speed of light, making black holes truly black in the sense that they emit no light of their own. However, matter falling toward a black hole gets heated to extremely high temperatures by compression and friction, creating bright accretion disks visible across the spectrum. If the black hole has a companion star, it can accrete material from the companion, producing X-ray binaries that reveal the black hole's presence. Isolated black holes are much harder to detect because they don't accrete and emit essentially no radiation. The question of whether Stevenson 2-18 will leave a neutron star or black hole depends on its evolutionary path between now and core collapse. If the star loses enough mass through winds to reduce its final mass below the threshold, probably around 15 to 20 solar masses depending on metallicity and rotation, it will likely produce a neutron star. If it retains more mass, either because mass loss declines or because the initial mass was higher than estimates suggest, a black hole becomes more likely. Some models predict that very massive stars can undergo direct collapse to black holes without producing bright supernova, a process called failed supernova that would leave no visible remnant. Recent observations of supernovae and their progenitors have revealed a puzzling pattern called the red supergiant problem. When astronomers examine pre-explosion images to identify supernova progenitors, they find that the most massive red supergiants seem to be missing from the list of Type 2. Supernova progenitors. Observed progenitors have estimated masses below about 16 solar masses, suggesting that more massive red supergiants either don't explode as Type 2p supernovae or undergo failed explosions that produce black holes directly. This pattern has significant implications for understanding stellar death and the black hole formation rate in the galaxy. One explanation for the red supergiant problem involves enhanced mass loss during the red supergiant phase that strips massive stars of their hydrogen envelopes, causing them to evolve blueward before explosion. These stars would then explode as Type Tacitus b, IB, or X supernovae depending on how much envelope mass remains, rather than Type 2p. Stevenson 2-18's high mass loss rate makes it a candidate for this evolutionary path, potentially transforming into a yellow or blue supergiant before core collapse. Alternatively, some massive red supergiants might collapse directly to black holes without ejecting their envelopes, producing optical transients much fainter than typical supernovae, or even remaining completely dark. The fate of Stephenson 2-18 remains uncertain until we better understand mass loss physics and the explosion mechanism for massive stars. What we can say with confidence is that the star has at most a few 100,000 years remaining before core collapse, and possibly much less if it's already in late stages of silicon burning. When it does explode or collapse, the event will provide invaluable data about stellar death and the formation of compact objects. If we're fortunate enough to detect the neutrino burst and observe the explosion in real time, it could answer fundamental questions about supernova physics that have puzzled scientists for decades. Mass loss from red supergiants doesn't always proceed smoothly and steadily through stellar winds. Sometimes these dying stars experience violent episodes where huge chunks of their atmospheres get ejected in discrete events that dwarf the normal mass loss rate. Betelgeuse provided a spectacular example of this phenomenon during its great dimming of late 2019 and early 2020, when the star lost more than 2/3 of its brightness over just a few months. What astronomers witnessed wasn't an imminent supernova as some media outlets breathlessly reported, but rather a surface mass ejection on a scale never before observed in real time. Andrea Dupree and her team at the Harvard-Smithsonian Center for Astrophysics used the Hubble Space Telescope to track Betelgeuse through the dimming event, obtaining ultraviolet spectra that revealed what was happening. The observations showed that sometime in early 2019, a massive convective cell rose to the star's surface in the southeastern region. This wasn't just ordinary convection, but a truly enormous bubble of hot material carrying tremendous energy from deep inside the star. As this bubble reached the photosphere, it created a shock wave that propagated outward through the extended atmosphere. The Hubble data captured material moving at roughly 200,000 miles per hour as it left Betelgeuse's surface and travelled through the atmosphere. This gas was super hot, glowing with brightness 2 to 4 times greater than the star's normal luminosity in that region. The combination of the convective upwelling and an outward pulsation phase created perfect conditions for ejecting a huge mass of material. The gas continued moving outward for millions of miles until it cooled enough for dust grains to condense. These grains formed a cloud that blocked light from about a quarter of Betelgeuse's visible surface, creating the dramatic dimming that captured public attention. The mass ejected in this single event could represent anywhere from 3% to 128% of Betelgeuse's annual stellar wind mass loss, depending on which estimate you trust. That's an enormous range reflecting the difficulty of measuring exactly how much material got ejected, but even the lower estimates indicate a substantial discrete mass loss episode. If such events occur periodically, they could contribute as much material to the circumstellar environment as the steady stellar wind, fundamentally changing how we understand red supergiant mass loss. What makes this observation so valuable is that astronomers caught it happening in real time rather than inferring past events from circumstellar structures. Betelgeuse sits only about 550 light-years away, close enough that instruments like Hubble can resolve surface features and track changes over weeks and months. The star's photosphere is so large and nearby that interferometric observations can actually image its mottled surface showing convective cells and bright spots. When the Great Dimming occurred, telescopes worldwide turned their attention to this familiar star, creating an unprecedented dataset spanning multiple wavelengths from radio through X-rays. Ground-based observations using the Very Large Telescope in Chile captured stunning images showing how Betelgeuse's southern hemisphere darkened progressively from December 2019 through March 2020. These images provided visual confirmation of what spectroscopy suggested, that the dimming resulted from dust obscuration rather than a fundamental change in the star's luminosity. Infrared observations showed no significant drop in total energy output, indicating the star itself wasn't actually getting dimmer, just blocked by intervening material. The aftermath of the surface mass ejection left Betelgeuse in an altered state that persists years later. The photosphere became cooler and less dense than before the event. Temperature measurements using spectral line ratios indicated a drop of at least 250 Kelvin, and possibly more during the dimming. The chromosphere also showed reduced density in post-event observations. More dramatically, the star's fundamental pulsation period of 400 days, which had been stable for nearly 2 centuries of observations, completely disappeared after the Great Dimming and got replaced by a new period around 200 days. This mode switching demonstrates how violent the surface mass ejection was, disturbing the star's structure enough to fundamentally alter its pulsation behaviour. Theoretical models suggest that large convective plumes coinciding with pulsation phases can inject enough energy into the envelope to change oscillation modes. The fact that Betelgeuse's pulsations haven't returned to the old pattern years after the event indicates the star hasn't fully recovered its pre-ejection equilibrium. Recent observations from April 2023 showed the chromosphere brightening again to levels comparable with the pre-dimming state, suggesting another hot convective region may be preparing for a similar outburst. The mechanism behind these surface mass ejections connects to the fundamental instability of red supergiant atmospheres. These stars exist at the edge of what stellar structure can support, with enormous radii, cool surfaces, and violent convection creating conditions prone to eruptions. Theoretical work by Jim Fuller and others has shown that wave heating in massive star envelopes can drive pre-supernova outbursts, potentially explaining some of the circumstellar material observed around supernova progenitors. When a large convective cell reaches the surface, it can launch acoustic waves and shocks that deposit energy in the outer atmosphere, heating and accelerating material to escape velocity. Veilsa Canis Majoris provides additional evidence for episodic mass loss from red supergiants. High-resolution imaging of this extreme star reveals an incredibly complex circumstellar environment, with arcs, knots, filaments, and clumps distributed over thousands of astronomical units. The structures show different velocities and compositions, suggesting they formed during distinct ejection events spread over thousands of years. Some of the knots contain surprisingly large masses, equivalent to several times Jupiter's mass, ejected in single episodes. The three-dimensional morphology reconstructed from observations shows material moving in multiple directions, rather than smooth spherical expansion, indicating localized surface eruptions. Stevenson 2018 likely experiences similar episodic mass loss events given its extreme properties and high overall mass loss rate. The strong master emission and unusual spectral energy distribution could partly result from past eruptions, creating density enhancements in the circumstellar envelope. Without Betelgeuse's proximity, allowing direct imaging and detailed monitoring, we can't observe these events on Stephenson 218 directly, but the physical conditions should be similar or even more extreme given the larger size and higher luminosity. If anything, Stephenson 218's position near theoretical size limits might make it more prone to violent instabilities. The question of whether surface mass ejections are common or rare among red supergiants remains open because we've only recently developed the capability to observe them. Betelgeuse has been intensively studied for decades, yet the Great Dimming was the first confirmed surface mass ejection caught in progress. Looking back through historical light curves, astronomers identified another possible dimming event in 1984 through 1986 that might have resulted from similar processes. If surface mass ejections occur once every few decades for stars like Betelgeuse, and we've only been watching carefully for a short time, we've barely scratched the surface of understanding their frequency and typical properties. The implications for stellar evolution are significant, because these events can potentially remove substantial envelope mass in ways not captured by steady wind mass loss prescriptions used in stellar models. if a red supergiant ejects 10% of its envelope mass in a single event, that could change its subsequent evolution as much as millions of years of normal winds. The star might transition to bluer spectral types faster, or remain on the red supergiant branch longer, depending on how mass loss timing affects core burning. Surface mass ejections might also help explain the scatter in red supergiant properties within clusters where stars started with similar masses. For Stevenson 218 specifically, we should expect that its extreme mass loss rate includes contributions from both steady winds and episodic eruptions. The maser observations indicating the highest mass loss in the Stephenson 2 cluster might partly reflect recent surface mass ejection events rather than purely continuous outflow. The circumstellar envelope structure probably contains shells and clumps from past ejections, superimposed on the underlying wind, creating the complex environment that makes the star difficult to characterize. Future monitoring with infrared telescopes might catch Stephenson 2T18 during a major eruption, providing data on how these events scale with stellar luminosity and size. While typical core collapse supernovae release around 10 to the 51 ergs of kinetic energy, some massive star explosions produce 10 to 100 times more energy, earning them the designation hypernova. These ultra-energetic explosions are associated with the most massive stellar progenitors, rapid rotation, and in some cases the production of long-duration gamma-ray bursts. Whether Stephenson 218 could explode as a hypernova rather than an ordinary supernova depends on details of its rotation, magnetic fields, and final core mass that we cannot directly observe. The collapsor model explains hypernovae and their associated gamma-ray bursts through a specific sequence of events during core collapse. When a rapidly rotating massive star exhausts its nuclear fuel, the iron core collapses to form a black hole rather than a neutron star. The high rotation rate means infalling material doesn't fall straight into the black hole, but instead forms a rapidly accreting disk around it. This disk can reach temperatures of billions of degrees and densities where nuclear reactions proceed explosively, releasing enormous energy. The accretion disk launches twin relativistic jets along the rotation axis through processes involving magnetic fields threading the disk and black hole. These jets carry matter at velocities exceeding 99% of light speed, ploughing through the overlying stellar envelope. If the jets successfully punch through the star's surface, they create a burst of gamma radiation lasting seconds to minutes, the signature of a long-duration gamma-ray burst. The jet interaction with stellar material also drives an extremely energetic explosion that shatters the star with kinetic energy far exceeding normal supernovae. Observations have firmly established the connection between hypernovae and gamma-ray bursts through events like GRB 980425, paired with supernova 1998 BW, and GRB 030329 paired with supernova 2003 DH. Spectra of these events show the characteristic broad absorption lines indicating material moving at 10% of light speed, or faster, dramatically higher than the few percent typical of regular supernovae. The spectral evolution reveals these are type Ike supernovae, meaning they've lost their hydrogen and helium envelopes, leaving only the carbon-oxygen core exposed. The envelope stripping is critical for allowing relativistic jets to escape. A star that retains its hydrogen envelope presents too much material for the jets to penetrate before they lose energy through interactions with stellar gas. Only stars stripped down to their cores, either through stellar winds or binary mass transfer, can produce the collimated relativistic outflows needed for observable gamma-ray bursts. This is why gamma-ray burst progenitors are thought to be Wolf-Rayet stars or similar objects that have shed their outer layers through previous evolution. Stephenson 2-18's status as a red supergiant with presumably intact hydrogen envelope makes it an unlikely gamma-ray burst progenitor in its current state. The enormous envelope extending to 10 astronomical units would contain far too much mass for any jet to penetrate. However, if the star's high mass loss rate continues or accelerates, it might strip away the envelope before core collapse, transforming the star into a hot supergiant or Wolf-Rayet star. In that case, hypernova explosion becomes possible if the star retains enough angular momentum to form an accretion disk and launch jets. The rotation rate of Stephenson 2-18 is unknown because we cannot resolve surface features or measure rotational broadening in spectral lines given the distance and obscuration. Red supergiants generally rotate slowly compared to main sequence stars because angular momentum gets redistributed and lost as the star expands. A star that starts with rapid rotation on the main sequence typically slows dramatically when it becomes a red supergiant as the envelope expands to hundreds of times its original radius. Conservation of angular momentum means rotation rate drops proportionally, turning fast rotators into slow ones. However, some mechanisms could maintain higher rotation in red supergiants. Binary mass transfer might spin up a star that accretes material from a companion. Internal magnetic fields could transport angular momentum from the core to the envelope, keeping surface rotation higher than expected. Mergers between stars could create rapidly rotating massive stars that retain high spin even after expanding. Without direct measurements, we can't determine whether Stephenson 2-18 has rotation sufficient for hypernova production, but standard evolution suggests it probably rotates too slowly. The energy budget for hypernovae comes partly from the rotational energy of the black hole and accretion disk. A maximally spinning black hole contains enormous rotational energy that can be extracted through the Blandford-Zernayek process, where magnetic fields threading the event horizon tap into the rotation to drive jets. The efficiency of this energy extraction depends on the black hole's spin parameter, with faster rotation allowing more efficient jet production. Simulations show that collapsor jets can achieve the luminosities and durations observed in gamma-ray bursts if the black hole spin is high enough. The total energy budget includes contributions from accretion, black hole spin, and radioactive decay of nickel-56 synthesized in the explosion. The nickel production occurs in several locations, including the accretion disk itself, where extreme temperatures allow explosive nucleosynthesis. The amount of nickel produced determines the optical light curve brightness weeks to months after the explosion, when radioactive decay powers the glow. Hypernovae synthesize more nickel than normal supernovae because of the higher energy available, creating exceptionally bright optical transients. For an explosion to qualify as a hypernova, the kinetic energy typically needs to exceed 10 to the 52 ergs, about 10 times a normal core collapse supernova. This energy accelerates several solar masses of material to velocities of 30,000 km per second or more. The expansion velocity can be measured spectroscopically through the width of absorption lines, with broader lines indicating faster expansion. Hypernova spectra show lines several times broader than normal supernova, providing direct evidence for the enhanced explosion energy. Whether we would observe a gamma-ray burst from Stevenson 2-18, even if it underwent hypernova explosion, depends on the jet orientation. The jets have opening angles of only a few degrees, meaning they cover a tiny fraction of the sky. Unless one of the jets happens to point toward Earth, we won't see the gamma-ray emission, even though the explosion itself is still hypernova-level energetic. Statistical estimates suggest that for every observed gamma-ray burst, there are hundreds of similar explosions where the jets point in other directions and go undetected in gamma-rays. The distance of 20,000 light-years means that if Stephenson 2-18 did produce a gamma-ray burst pointed at Earth, it would be detected easily by satellites monitoring the sky. The burst would be far brighter than typical cosmological gamma-ray bursts that come from billions of light-years away. In fact, a gamma-ray burst from this distance could potentially deliver enough radiation to affect Earth's atmosphere, though the jet's narrow collimation means most of the planet would be unaffected. This has led to speculation that past gamma-ray bursts might have contributed to some mass extinction events in Earth's history. The more likely outcome for Stephenson 2-18 is an ordinary Type II supernova, where the star explodes with its hydrogen envelope intact and produces a neutron star or black hole without relativistic jets. The visual display would still be spectacular, easily visible to the naked eye despite the large distance, but without the exotic physics of hypernova explosions. The supernova would reach peak brightness comparable to the full moon, or possibly brighter, dominating the night sky for weeks before fading over months. The light curve would show the characteristic plateau of Type II P supernovae as the ejected envelope recombines. Understanding how Stephenson 2-18 loses mass requires diving into the physics of stellar winds, the continuous outflow of material driven by radiation pressure and other forces. Unlike the episodic surface mass ejections discussed earlier, stellar winds represent the steady background mass loss that operates continuously throughout the red supergiant phase. The combination of high luminosity, cool surface temperature, and low surface gravity creates perfect conditions for driving powerful winds that carry away significant fractions of stellar mass. The mechanism begins with radiation pressure on dust grains that form in the cool outer atmosphere. Photons streaming outward from the stellar interior interact with these grains through scattering, transferring momentum with each collision. Individual photons carry tiny momentum, but the star emits so many that the cumulative radiation pressure can accelerate dust grains to velocities exceeding the surface escape velocity. Once the grains start moving outward, they collide with gas atoms and molecules, dragging them along through friction in a process called grain-gas coupling. The efficiency of this mechanism depends critically on dust formation, because if grains don't condense, radiation pressure can't gain leverage on the gas. Dust formation requires temperatures below about 1000 to 1500 Kelvin, depending on grain composition. Silicate grains, composed of silicon-oxygen compounds, form around 1000 Kelvin, while carbon-based grains require slightly different conditions. For oxygen-rich red supergiants like Stephenson 218, silicates are the primary dust species, evident from the strong 10 and 18 micrometer emission features in infrared spectra. The pulsations observed in red supergiants play a crucial role in enhancing dust formation and mass loss. When the star pulsates outward, the photosphere expands and cools, temporarily dropping the temperature in regions where dust can condense more efficiently. The pulsation also creates density waves that compress gas, increasing the density where grain nucleation occurs. Higher density means more frequent collisions between atoms, speeding up the growth of condensation nuclei into larger grains capable of being driven by radiation pressure. This pulsation-enhanced dust formation can increase mass loss rates by factors of several compared to steady-state winds. Once dust grains accelerate outward, they must efficiently couple to the gas to drive the wind. The coupling occurs through collisions between grains and gas atoms, with each collision transferring momentum. The efficiency depends on the grain size distribution, because very small grains have large surface area relative to mass, maximizing collision frequency, while very large grains have too much inertia and don't accelerate as effectively. Observations and models suggest typical grain sizes of around 0.1 to 1 micrometer, roughly the wavelength of visible to near-infrared light. The velocity profile of stellar winds can be measured through spectroscopic observations of absorption or emission features. For red supergiants, terminal wind velocities typically range from 10 to 30 kilometers per second, much slower than the thousands of kilometers per second seen in hot star winds. This slower velocity reflects the different driving mechanism, with radiation pressure on dust being less efficient than radiation pressure on spectral lines that drives hot star winds. Despite the lower velocity, red supergiant winds carry away substantial mass because the mass loss rate is so high. The mass loss rate itself can be estimated through several methods. One approach uses infrared excess, the amount by which the star's infrared emission exceeds what a bare photosphere would produce. This excess comes from dust in the wind absorbing stellar radiation and re-emitting it at infrared wavelengths. By modelling the spectral energy distribution and fitting dust emission, researchers can constrain how much dust exists, which relates to the mass loss rate if you assume a gas-to-dust ratio. Typical gas-to-dust ratios around 200 mean that for every unit of dust mass, there are 200 units of gas mass. Another method uses master emission as a diagnostic of mass loss rate, because masses trace specific density and temperature conditions in the wind. Water masses form at particular radii, where temperature drops to about 1000 Kelvin and density is high enough for collisional pumping. The strength and distribution of maser emission constrains the density structure, which depends on mass loss rate and wind velocity. Silicon monoxide masses probe slightly different conditions closer to the star. Combining multiple maser species provides better constraints than either alone. The mass loss rate of 1.35 times 10 to the minus 5 solar masses per year for Stevenson 218 ranks among the highest known for red supergiants. To put this in perspective, the Sun loses mass at about 10 to the minus 14 solar masses per year through the solar wind, more than 8 orders of magnitude slower. In just 74,000 years, Stevenson 218 sheds an entire solar mass worth of material. Over the full red supergiant phase lasting perhaps 1 million years, the star could lose 10 to 15 solar masses, fundamentally altering its structure and affecting its final fate. The fate of this ejected material shapes the circumstellar environment and eventually enriches the interstellar medium. Close to the star, the wind consists of hot gas and small dust grains moving outward at tens of kilometers per second. As material flows away from the star, it cools further and molecules begin forming. Water, carbon monoxide, silicon monoxide, and other molecules appear at different radii depending on their formation chemistry. These molecules emit characteristic infrared and radiospectral features used to study wind properties. Further out, the wind eventually encounters the surrounding interstellar medium, creating a shock front where the two gases collide. The standoff distance depends on the mass loss rate, wind velocity, and interstellar medium density and pressure. For extreme mass losers like Stevenson 218, this interaction region might lie several parsecs from the star, well beyond any structure visible in current images. The shocked wind creates a bubble of hot gas that could eventually be detected in X-rays if observations sensitive enough are conducted. The chemical composition of stellar wind material reflects nuclear processing in the star's interior, plus whatever modifications occur in the atmosphere. For red supergiants, the wind is mainly hydrogen with helium and trace amounts of heavier elements produced in fusion reactions. Elements like carbon, nitrogen, and oxygen might show enhanced abundances if convective dredge-up has brought processed material to the surface. These enriched winds will eventually become part of molecular clouds where future stars form, incorporating the products of stellar nucleosynthesis into later generations. Magnetic fields might play a role in red supergiant winds, though evidence remains limited. Theoretical models suggest weak large-scale magnetic fields threading the atmosphere could help channel outflow or create structure. Observations of circular polarization in spectral lines might reveal magnetic field strength and geometry, but such measurements are extremely difficult for distant obscured objects like Stephenson 2-18. Nearby red supergiants like Betelgeuse show hints of magnetic fields at the few Gauss level, weak compared to sunspots but potentially significant over stellar scales. Studying Stephenson 2-18 and similar extreme stars presents extraordinary technical challenges because these objects actively hide themselves from view. The combination of enormous distance, heavy interstellar extinction, and thick circumstellar envelopes means that many standard astronomical techniques simply don't work or require specialized approaches. Understanding how astronomers extract information from such difficult targets reveals both the power of modern instrumentation and the limitations we still face. The 20,000 light-year distance places Stephenson 2-18 firmly in the infrared-only category for ground-based observations. At visible wavelengths, the galactic dust between us and the star creates so much extinction that essentially no light reaches us. Extinction measures how much light gets absorbed or scattered out of the line of sight, typically quantified in magnitudes. A visual extinction of 10 magnitudes means only 1/10,000th of the light gets through, while extinction of 20 magnitudes reduces transmission to 1 part in 100 million. Stephenson 2-18 likely suffers visual extinction exceeding 30 magnitudes, rendering it completely invisible to optical telescopes. Infrared wavelengths penetrate dust much better than visible light because dust grains scatter and absorb shorter wavelengths more efficiently. At near-infrared wavelengths around 1 to 2 micrometers, extinction drops by factors of 5 to 10 compared to visible light. At mid-infrared wavelengths around 10 micrometers, extinction becomes almost negligible unless the dust column is extraordinarily dense. This wavelength dependence allows infrared telescopes to peer through galactic dust that completely blocks visible light, revealing objects that would otherwise remain hidden. The first infrared surveys that detected Stephenson 2-18 used relatively modest telescopes but specialized detector arrays sensitive to infrared radiation. Early infrared astronomy required cooling detectors to liquid nitrogen or liquid helium temperatures to reduce thermal noise that would otherwise swamp faint signals. Modern infrared cameras use improved detector materials and cooling systems that can reach just a few degrees above absolute zero, dramatically improving sensitivity. These technological advances have opened up previously inaccessible parts of the galaxy to study. Getting spectra of Stephenson 2-18 requires large telescopes equipped with infrared spectrographs. Near-infrared spectrographs working at 1 to 2.5 micrometers can measure molecular absorption bands from water, carbon monoxide, and silicon monoxide in the stellar atmosphere. These features reveal temperature and composition, though interpreting them requires accounting for both interstellar and circumstellar absorption. Mid-infrared spectrographs covering 5 to 25 micrometers access continuum emission from dust and atomic emission lines from species like neon and sulfur. The Australia Telescope Compact Array observations that derived Stevenson 218's luminosity and temperature used millimeter wave interferometry to map dust emission. Interferometry combines signals from multiple telescopes separated by large distances to achieve angular resolution equivalent to a telescope the size of the separation. This technique allows measuring brightness distribution on scales of thousandths of an arc-second, far beyond what single telescopes can achieve. The dust emission at millimeter wavelengths traces the coolest circumstellar material farthest from the star. Radio observations access the matter emission that provides crucial diagnostics of the wind. Water masers at 22 GHz and silicon monoxide masers at 43 and 86 GHz require specialized receivers and can achieve extremely high spectral resolution to measure velocity structure. Very long baseline interferometry uses radio telescopes separated by thousands of kilometers to achieve milliarc-second resolution, potentially resolving the master emission regions. For Stevenson 2-18, such observations could map the inner wind structure where masses form. Infrared interferometry offers another approach to studying red supergiant surfaces and near environments. Instruments like the VLTI interferometer combine light from multiple 8-meter telescopes to achieve resolution equivalent to a telescope 100 meters across. This resolves stellar surfaces for nearby red supergiants and can probe circumstellar structure for more distant objects. Future interferometric observations might resolve Stevenson 218's photosphere directly if atmospheric conditions and instrumental capabilities improve sufficiently. Space-based infrared telescopes avoid atmospheric absorption that blocks some infrared wavelengths from reaching ground-based observatories. The Spitzer Space Telescope observed Stevenson 2-18 in mid-infrared bands before its mission ended, capturing images showing the extended envelope. The James Webb Space Telescope now provides far greater sensitivity and resolution in infrared wavelengths, opening new possibilities for studying extreme red supergiants. Webb's near-infrared and mid-infrared cameras could image circumstellar shells and measure spectral features with unprecedented detail. Future observations will continue refining our understanding of Stevenson 2-18's properties. Improved distance measurements using parallax from the Gaia mission or other techniques would reduce uncertainty in derived luminosity and radius. Detailed spectroscopic monitoring could track variability and search for evidence of pulsation modes. Long baseline interferometry might resolve surface features or measure angular diameter directly. Each new data set constrains models and tests whether our theoretical understanding correctly describes these extreme objects. The challenges of observing Stevenson 2-18 illustrate why so much remains uncertain about its properties. Every measurement faces systematic uncertainties from distance, extinction, circumstellar emission, and model assumptions. Progress requires multiple independent techniques that probe different aspects of the star's structure. As instrumentation improves and observing time accumulates, the picture will sharpen, but given the inherent difficulties, some questions may remain unanswered until we develop entirely new observational capabilities. Stevenson 2-18 may be the largest known star, but it's not alone in the realm of extreme stellar objects. Several other stars compete for various superlatives including largest radius, highest luminosity, or most massive, each pushing against theoretical limits in different ways. Comparing these objects reveals patterns in stellar evolution and the diversity of outcomes possible for massive stars. UY Scuti held the title of largest known star for several years until more accurate measurements from the Gaia space mission revised its parameters downward. Early estimates placed its radius at 1,708 solar radii based on indirect distance measurements and assumptions about luminosity. However, Gaia's precise parallax measurements gave a much closer distance than previously thought, which reduced the derived luminosity and radius to about 755 solar radii. This dramatic revision illustrates the challenges of measuring stellar parameters for distant, heavily obscured objects, and reminds us that current measurements of Stevenson 2-18 could similarly be revised as better data becomes available. Virus Canis Majoris represents another extreme red supergiant with a radius around 1,420 solar radii, making it substantially smaller than Stevenson 2-18, but still enormous by any standard. Virus Canis Majoris is notable for its complex circumstellar environment, including arcs, knots, and filaments of ejected material visible in high-resolution images. These structures suggest episodic mass loss events, possibly from pulsation-driven outbursts that have created a non-spherical envelope. The star's variability and spectral features indicate it's in a highly unstable state, likely approaching the end of its red supergiant phase. Betelgeuse, the famous red supergiant in Orion, has a radius around 887 solar radii, much smaller than Stevenson 2-18 but far more accessible for detailed study. Betelgeuse lies only about 550 light-years away compared to 20,000 for Stevenson 2-18, allowing high-resolution interferometric imaging that reveals surface features and asymmetries. Recent dimming events where Betelgeuse dropped in brightness by more than a magnitude have fueled speculation about imminent core collapse, though astronomers believe the dimming resulted from dust ejection temporarily blocking light rather than indicating the star is about to explode. Antares, another well-known red supergiant, spans about 680 to 800 solar radii and displays characteristics typical of M-type supergiants, including strong mass loss and variability. Located in Scorpius at a distance around 550 light-years, Antares is bright enough to study in detail and serves as a comparison for understanding more distant objects. The star has a binary companion, a hot B-type star that orbits at a distance of about 850 astronomical units, providing opportunities to study how binary interactions might affect red supergiant evolution. Mu Cephei, also called Herschel's garnet star for its striking deep red colour, has a radius estimated between 972 and 1,260 solar radii. This star's spectral type around M2 makes it somewhat hotter than Stevenson 2-18's M6 classification, and its luminosity of around 300,000 solar luminosities places it in the same range. Mu Cephei shows semi-regular variations with periods around several hundred days, typical of red supergiant pulsations, and infrared observations reveal substantial circumstellar dust. HR 5171a presents an interesting case as it appears to be a contact binary system where the primary component is a yellow hypergiant with radius around 1060 to 1160 solar radii. The companion lies so close that the two stars may actually be in contact, sharing a common envelope. This system challenges traditional ideas about stellar evolution and mass loss, because interactions between the components can dramatically alter each star's evolution compared to isolated stars. Observations show the system brightening and fading over decades, possibly from pulsations or changes in the binary configuration. These comparisons reveal that extreme stellar radii are not unique to Stevenson 2-18, but represent a broader class of stars that have evolved to push against physical limits. The radii cluster in the range of 700 to 2,000 solar radii, suggesting some combination of stellar structure and mass loss, creates a natural upper limit in this regime. Stars that grow larger than this limit become increasingly unstable, with pulsations and mass loss working together to prevent further expansion or even cause contraction back to smaller radii. The luminosity range of these extreme stars spans from about 100,000 to more than 500,000 solar luminosities, with Stevenson 2-18 near the upper end. Higher luminosity drives stronger mass loss because radiation pressure scales with luminosity, creating more vigorous winds. The relationship between luminosity and mass loss rate follows roughly a power law, with mass loss increasing faster than luminosity, which means the most luminous stars also lose mass fastest. This creates a self-regulating mechanism where stars that grow too luminous shed mass rapidly, reducing their luminosity and preventing runaway growth. Temperature variation among red supergiants is relatively modest, with most falling in the range of 3,000 to 4,000 Kelvin. This narrow temperature range exists because cooler temperatures allow molecules to survive in the atmosphere, creating molecular absorption that reduces radiation pressure and stabilizes the structure. Hotter stars don't have molecules in their atmospheres and can't sustain the same mass loss mechanism, which forces them into different evolutionary channels. The temperature-luminosity relationship creates the characteristic diagonal band that red supergiants occupy on the Hertzsprung-Russell diagram. While we observe Stevenson 218's extended cool photosphere from afar, the true drama unfolds deep within the star where temperatures and pressures reach values that strain comprehension. The core currently burns helium into carbon and oxygen through the triple alpha process, where 3 helium nuclei fuse to create carbon at temperatures around 100 million Kelvin. This temperature seems incomprehensibly hot until you realize it's modest compared to the billions of Kelvin that await during later burning stages. The triple alpha process gets its name from alpha particles, which are helium nuclei containing 2 protons and 2 neutrons. The first step fuses 2 helium nuclei into beryllium-8, but this nucleus is unstable and quickly decays back to 2 helium atoms, unless a third helium nucleus collides with it first. When that rare 3-body collision occurs, carbon-12 forms in an excited state that decays to the ground state while emitting gamma rays. The energy release supports the core against gravitational collapse and generates the star's enormous luminosity. Carbon and oxygen accumulate in the core as helium burning proceeds, creating an inert CO core surrounded by a shell where helium fusion continues. This shell burning injects energy that maintains the envelope inflation, while the core itself produces no energy. The temperature and density in the core gradually increase as mass accumulates from the burning shell above. When conditions reach approximately 600 million Kelvin and densities exceed 10,000 grams per cubic centimeter, carbon ignition becomes possible. Carbon burning operates through several nuclear reaction pathways that depend sensitively on temperature. At around 600 million Kelvin, carbon-12 nuclei fuse to create neon-20, releasing helium as a byproduct. Alternative channels produce sodium-23 plus a proton, or magnesium-24 plus gamma rays. Each reaction releases several million electron volts of energy, which sounds like a lot until you consider that billions of reactions must occur every second in every cubic centimeter to maintain pressure against gravity. The energy generation rate from carbon burning scales extremely steeply, with temperature approximately as temperature to the 40th power in some regimes. This sensitivity means even small temperature changes cause enormous variations in energy production, creating potential instabilities. The core can't maintain smooth equilibrium, but instead experiences temperature fluctuations that drive convection and possibly pulsations. These convective motions transport freshly burned material away from the hottest regions and bring unburned fuel in, sustaining reactions. Neon burning follows carbon exhaustion, when the core contracts further and reaches temperatures around 1.2 billion Kelvin. At these temperatures, high-energy gamma rays possess enough energy to photodisintegrate neon-20 nuclei, breaking them apart into oxygen-16 and helium-4. This seems counterproductive, destroying neon rather than building heavier elements, but the liberated alpha particles immediately fuse with other neon nucleus, creating oxygen and magnesium. The net result transforms neon into heavier elements while releasing energy. Oxygen burning ignites around 1.8 billion Kelvin, fusing oxygen-16 nuclei through several channels. The primary products are silicon-28 plus helium, sulfur-32 plus gamma rays, and phosphorus-31 plus a proton. Like earlier stages, oxygen burning proceeds rapidly once ignited, exhausting the core oxygen in months to years. The ashes accumulate while the core contracts again, driving temperatures and densities higher in preparation for the final burning stage. Silicon burning represents the last nuclear energy source available to the star because it produces iron peak elements that have the highest nuclear binding energy. At temperatures exceeding 3 billion Kelvin, silicon undergoes photodisintegration into lighter nuclei, which then fuse in complex networks of reactions. The process builds up elements like titanium, chromium, manganese, and iron through successive alpha particle captures and other pathways. Iron 56 and nickel 56 dominate the final products because they're the most stable nuclei. The energy yield per reaction drops with each successive burning stage because heavier nuclei already have strong binding, and adding more nucleons releases less energy. Silicon burning produces only about 1/10 the energy per gram as hydrogen burning, forcing the core to consume fuel much faster to maintain pressure. This accelerating pace means the silicon burning phase lasts only days to weeks, a blink compared to the millions of years spent burning hydrogen. The star rushes toward its doom as the core fills with iron, the end of the nuclear road. Each burning stage leaves its signature in the core structure, creating the onion shell configuration that characterizes massive stars near core collapse. Moving outward from the iron core, you pass through shells of silicon, oxygen, neon, carbon, helium, and finally hydrogen. Each shell has distinct temperature, density, and composition, with thin transition zones where multiple burning processes occur simultaneously. This stratified structure is inherently dynamic because each shell's energy generation affects adjacent layers, creating complex feedback. The core mass grows throughout these burning stages as burning shells add material to the inert core below. A star with initial mass around 20 solar masses might develop an iron core around 1.3 solar masses, right at the Chandrasekhar limit, where electron degeneracy pressure can barely support the core. The precise core mass at collapse depends on the initial stellar mass, rotation, metallicity, and mass loss history. Stars that lose more envelope mass tend to develop smaller cores because less material is available to fall inward. The tremendous central densities compress electrons into a degenerate gas where quantum mechanical effects dominate. In ordinary matter, electrons occupy energy states determined by temperature, with many possible states available. In degenerate matter, density is so high that electrons fill all low-energy states, and the Pauli exclusion principle forces additional electrons into higher energy levels regardless of temperature. This creates pressure depending only on density, which can temporarily support the core against gravity. Neutrinos play an increasingly important role in the core as temperature rises. At billions of degrees, pair production creates electron-positron pairs that annihilate to produce neutrinos. These neutrinos escape the star freely, carrying away energy without contributing to pressure support. The neutrino losses accelerate core cooling and contraction, speeding the rush toward collapse. In the silicon burning stage, neutrino losses can exceed the nuclear energy generation rate, making neutrinos the dominant energy transport mechanism. The exact structure of Stephenson 2-18's core cannot be determined from external observations because we only see the photosphere. Whether the core has reached carbon burning, or still burns helium, or even begun later stages depends on the star's age and mass loss history. Stellar evolution models provide guidance but contain uncertainties in input physics like mass loss rates, convection efficiency, and rotation effects. Different models predict different internal structures for the same initial mass, making predictions uncertain. The uncertainty affects predictions for the star's remaining lifetime and final fate. If Stephenson 2-18's core has already burned through carbon and begun neon burning, collapse could occur in just thousands of years. If it's still early in helium burning, hundreds of thousands of years might remain. Without direct probes of the interior, we rely on surface observables like luminosity and temperature that provide limited constraints on core conditions. Only when the star explodes will we learn definitively what structure existed at core collapse. Massive stars like Stephenson 2-18 serve as the universe's primary factories for elements heavier than helium, synthesizing carbon, oxygen, silicon, iron, and dozens of other elements that make up planets, life, and everything in the world around us. The nuclear reactions occurring in their cores and envelopes create these elements through nucleosynthesis processes that build up the periodic table step by step. When these stars explode as supernovae, they scatter their products into space where future generations of stars and planets incorporate them. Hydrogen and helium were created in the Big Bang, but essentially all heavier elements formed inside stars. The first stars contained only these primordial elements: no carbon, no oxygen, no metals of any kind. When they finished their lives and exploded, they seeded the interstellar medium with the first heavy elements. Second-generation stars formed from gas enriched with these products, containing trace amounts of carbon and oxygen. Each successive generation increases the metallicity, the fraction of heavy elements present. Our Sun formed from material processed through several cycles of star formation and death over billions of years, giving it a metallicity about 2% by mass. Planets in our solar system inherited this composition, with rocky planets containing iron cores from ancient supernova explosions. The iron in your blood, the calcium in your bones, the oxygen you breathe all formed inside massive stars billions of years ago. Without stellar nucleosynthesis, neither Earth nor life would exist. Carbon production through helium burning in red supergiant cores proceeds at prodigious rates given the high luminosity. Stephenson 218 might produce a solar mass worth of carbon over the million-year red supergiant phase, though much of this carbon gets processed into heavier elements in later burning stages. Some carbon appears at the surface through convective dredge-up, enriching the stellar wind. Observations of carbon monoxide absorption in red supergiant spectra confirm carbon's presence in their atmospheres. Oxygen forms alongside carbon during helium burning when carbon nuclei capture additional helium nuclei. The ratio of carbon to oxygen depends on temperature and density, with higher temperatures favouring oxygen production. By the time helium burning finishes, the core typically contains roughly equal parts carbon and oxygen by mass, though ratios vary depending on initial stellar mass. This CO core represents the seed that will eventually collapse to form a neutron star or black hole. Nitrogen enrichment occurs through the CNO cycle that dominates hydrogen burning in massive stars. This cycle converts hydrogen to helium using carbon, nitrogen, and oxygen as catalysts. The reactions transform carbon into nitrogen, and convective mixing can bring nitrogen-enriched material to the surface. Red supergiants often show enhanced nitrogen abundances in their atmospheres from this process, with nitrogen to oxygen ratios elevated compared to initial composition. Silicon, sulfur, argon, calcium, and iron all form during later burning stages as the core progresses through neon, oxygen, and silicon burning. Each element appears at specific temperatures and densities corresponding to when particular nuclear reactions become energetically favourable. The final core composition reflects the last burning stage achieved before collapse, with iron dominating if silicon burning completes. The distribution of elements forms discrete shells surrounding the core, each marked by composition discontinuities. Explosive nucleosynthesis during the supernova creates many elements that don't form in normal stellar burning. When the shockwave passes through the stellar layers, temperatures and densities spike to extreme values for brief moments. These conditions allow rapid nuclear reactions that synthesize neutron-rich isotopes not accessible during hydrostatic burning. Elements heavier than iron, including gold, platinum, uranium, and others, require neutron capture processes that occur during supernova explosions or neutron star mergers. The radioactive isotope nickel-56 produced in the explosion powers the supernova light curve through its decay chain. Nickel-56 decays to cobalt-56 with a half-life of 6 days, and cobalt-56 decays to stable iron-56 with a 77-day half-life. The gamma rays released during these decays deposit energy in the expanding ejector, keeping it hot and luminous for months. The amount of nickel-56 synthesized determines the peak brightness and light curve shape, with more nickel creating brighter supernovae. Isotope ratios in supernova ejecta provide diagnostics of the explosion physics because different burning conditions produce different isotopic abundances. For instance, alpha-rich freeze-out during silicon burning creates specific isotope patterns different from normal freeze-out. Measuring isotopes in supernova remnants tests models of nuclear physics under extreme conditions not reproducible in laboratories. These measurements require high-resolution spectroscopy to resolve individual isotope features. The total mass of heavy elements ejected by a single supernova can reach several solar masses, with most mass in oxygen, carbon, neon, and magnesium. Iron peak elements typically amount to tenths of a solar mass, while rare heavy elements contribute negligibly to the mass budget, but are important for their unique properties. A galaxy like the Milky Way experiencing a few supernovae per century accumulates significant heavy element enrichment over billions of years, progressively increasing metallicity. When Stephenson 218 explodes, it will add its products to the galactic inventory, enriching molecular clouds where future stars form. The expanding supernova remnant will create a cavity in the interstellar medium, compressing surrounding gas and potentially triggering new star formation. The ejected elements will mix with existing gas over thousands of years, homogenizing the composition. Eventually, the enriched material participates in creating a new generation of stars that will continue the cycle. After Stephenson 218's supernova fades, the central remnant will be either a neutron star or black hole depending on the collapsing core mass. These two outcomes represent fundamentally different end states governed by different physics, yet both create objects almost beyond human comprehension in their extremity. Understanding the physics of neutron stars and stellar mass black holes reveals what awaits stars massive enough to undergo core collapse. Neutron stars pack between 1.4 and 2.1 solar masses into spheres roughly 20 kilometers across, creating average densities matching atomic nuclei. A teaspoon of neutron star material would weigh about 1 trillion kilograms on Earth, assuming you could somehow bring it here without it immediately exploding from decompression. The matter exists in states impossible to replicate in terrestrial laboratories, with densities so high that atomic structure breaks down entirely. The interior structure of neutron stars remains uncertain because we can't observe it directly, and nuclear physics becomes uncertain at such densities. The outer layers form a solid crust of neutron-rich nuclei in a lattice, somewhat like extreme versions of atomic nuclei found in normal matter. Deeper layers transition to a neutron superfluid where neutrons flow without viscosity. The core might contain exotic matter including hyperons, quarks, or other particles that don't exist in ordinary conditions. The maximum mass for neutron stars depends on the equation of state, the relationship between pressure and density in ultra-dense matter. Observations of massive neutron stars around 2 solar masses constrain possible equations of state by ruling out models that cannot support such masses. The recent observation of neutron star merger GW 170817 provided additional constraints from the gravitational wave signal that encodes information about neutron star deformability and equation of state. Black holes form when the collapsing core exceeds the maximum neutron star mass, roughly 2 to 3 solar masses depending on the equation of state. Once matter compresses beyond this limit, no known force can halt further collapse. The object shrinks inside its Schwarzschild radius, where escape velocity equals light speed. The resulting black hole has an event horizon from which nothing escapes, making it truly black in that it emits no radiation. The size of stellar mass black holes scales directly with mass, at about 3 kilometers per solar mass for the Schwarzschild radius. A 5 solar mass black hole has an event horizon roughly 15 kilometers across, comparable to a city. The enormous density comes from all the mass being concentrated at the singularity in the center, though general relativity suggests the singularity is where our physical theories break down rather than a real physical object. Black holes can spin up to the maximum rate where the event horizon surface moves at light speed, described by a dimensionless spin parameter between 0 and 1. Newly formed black holes from core collapse typically have moderate spin inherited from the progenitor star's rotation. The exact spin depends on angular momentum distribution in the collapsing core and how much falls back onto the black hole afterward. Rapidly spinning black holes have different properties, including a smaller event horizon and an ergosphere where space-time itself rotates. The distinction between neutron stars and black holes has observational consequences. Neutron stars can be detected as pulsars if their magnetic fields are strong and rotation axis is misaligned with the magnetic axis. The rotating magnetic field creates beams of radiation that sweep across space like lighthouse beams. Black holes don't emit beams and are invisible unless they accrete matter or affect companions through gravity. Isolated black holes are essentially undetectable with current technology. In binary systems, both neutron stars and black holes can accrete material from companion stars, creating X-ray sources observable across the galaxy. The accreted matter heats to millions of degrees as it spirals inward, emitting X-rays before disappearing into the compact object. X-ray binaries provide most of our information about stellar mass black holes because the accretion makes them visible. Studying their X-ray spectra and variability reveals properties of the black holes, including mass and spin. Gravitational wave astronomy has revolutionized the study of compact objects by detecting mergers between neutron stars and black holes. The LIGO and Virgo detectors observe ripples in spacetime created when these objects spiral together and merge, releasing enormous energy in gravitational radiation. Each detection provides information about masses, spins, and merger dynamics that test general relativity and equation of state models. Whether Stevenson 2-18 leaves a neutron star or black hole depends on uncertain mass loss and core mass evolution that we can't directly observe. The star's current total mass might be 15 to 25 solar masses based on initial mass estimates and mass loss history, but the core mass is what matters for the remnant. If the core at collapse is below about 2 to 3 solar masses, a neutron star forms. Above this threshold, a black hole is inevitable, The explosion mechanism might influence the outcome because fallback of ejecta onto the neutron star can push it over the mass limit. In some models, neutrino-driven explosions initially form neutron stars that then accrete several solar masses of fallback material and collapse to black holes seconds later. This delayed collapse could affect the supernova observables and remnant properties. Simulations show a range of outcomes depending sensitively on initial conditions and explosion physics. Stephenson 218 stands as testament to the extreme conditions possible in stellar evolution, a star so large that human imagination struggles to grasp its scale. 20,000 light-years away in the constellation Scutum, hidden behind curtains of galactic dust, this dying giant burns through its final nuclear fuel while shedding mass in powerful winds that create complex circumstellar structures. Whether it truly holds the record as the largest star ever found remains uncertain, because measurements depend on distance estimates and models with substantial uncertainties. But regardless of exact rankings, Stephenson 2-18 represents stellar physics pushed to its limits. The journey from molecular cloud to red supergiant took this star through millions of years of evolution, from gravitational collapse into a protostar, through the main sequence burning hydrogen in its core, and finally into the red supergiant phase where it now resides. Each stage left its imprint on the star's structure and composition, building up the onion-like shells of processed material that will eventually be expelled in a supernova explosion. The star's membership in, or near, the Stephenson 2 cluster connects it to dozens of other massive stars sharing similar fates, all created in the same burst of star formation and now dying together. Mass loss dominates the final chapters of Stephenson 218's existence, with winds carrying away solar masses of material over the red supergiant phase. This mass loss shapes not only the star's future evolution, but also enriches the surrounding interstellar medium with heavy elements forged in nuclear burning, providing raw materials for future generations of stars and planets. The water mazes, silicate emission, and infrared excess all signal the intensity of this mass loss, making Stephenson 218 one of the most extreme mass losers known. Episodic surface mass ejections like those observed on Betelgeuse might contribute substantially to the total mass loss, creating the clumpy circumstellar structures we observe. The coming supernova will mark both an ending and a beginning, destroying the star that created it while seeding the galaxy with carbon, oxygen, silicon, and iron that will become incorporated into new cosmic structures. Whether the remnant will be a neutron star or black hole depends on details we cannot yet determine, but either outcome represents a fascinating endpoint where matter exists in states impossible to recreate in terrestrial laboratories. The explosion might be visible from Earth as a brilliant new star in the night sky, rivaling the brightest objects visible and providing astronomers with an unprecedented opportunity to study stellar death in real time. The question of whether Stephenson 218 could produce a hypernova rather than ordinary supernova adds another layer of uncertainty to predictions. If the star somehow retains rapid rotation and strips its envelope before collapse, it might generate relativistic jets and a gamma ray burst alongside enhanced explosion energy. The collapsor model shows how rotating massive stars can produce these most energetic explosions in the universe, though the requirements for hydrogen envelope stripping and high angular momentum make such outcomes unlikely for typical red supergiants. Understanding stars like Stephenson 218 requires pushing observational technology to its limits, using infrared telescopes to penetrate obscuring dust, radio interferometry to measure maester emissions, and theoretical models to interpret the complex signals we receive. Each new observation refines our picture of these objects, sometimes confirming expectations and sometimes revealing surprises that challenge theoretical understanding. The field continues to evolve as new instruments come online and techniques improve, promising deeper insights into stellar physics and the life cycles of massive stars. The physical processes governing mass loss remain incompletely understood despite decades of study. Radiation pressure on dust grains clearly drives stellar winds, but the details of grain formation, growth, and coupling to gas involve complex physics not yet modelled from first principles. Pulsations enhance mass loss through density waves and temperature variations, while large convective cells can launch episodic eruptions that dwarf the steady wind. Magnetic fields might channel outflows or create structure in the circumstellar environment. Each of these mechanisms contributes to creating the mass loss rates we observe. Comparing Stevenson 2-18 with other extreme red supergiants reveals both commonalities and differences that constrain models. Stars like VY Canis Majoris and Betelgeuse show similar characteristics, including high luminosity, cool temperatures, massive winds, and complex circumstellar structures. Yet each star displays unique properties reflecting differences in mass, age, metallicity, rotation, and evolutionary history. The diversity within the red supergiant population indicates that multiple paths lead to these extreme states, with initial conditions and mass loss history determining which path each star follows. The Stevenson 2 cluster provides crucial context for understanding Stevenson 2-18 by showing that such extreme objects arise from specific star formation environments. The cluster's age of 14 to 20 million years and its rich population of red supergiants indicate a burst of massive star formation that created dozens of stars now reaching their endpoints simultaneously. Understanding why this cluster formed so many massive stars compared to typical clusters could reveal important clues about the conditions required for producing the most massive stars in the galaxy. The interior physics of Stevenson 2-18 remains hidden from direct observation, but stellar evolution models predict complex shell-burning structures that progressively build up heavier elements from hydrogen to iron. Each burning stage occurs faster than the last as the core contracts and heats, accelerating the star toward its inevitable collapse. The exact timing depends on uncertainties in mass loss, convection, rotation, and nuclear reaction rates that make precise predictions impossible with current understanding. Neutrino astronomy might someday detect the neutrino burst from Stevenson 2-18's core collapse hours before the optical supernova appears, providing advance warning and unique information about collapse physics. The neutrinos carry detailed imprints of conditions in the collapsing core, encoding information about temperature, density, and composition that can't be obtained any other way. Detecting and analysing this burst would revolutionise our understanding of core collapse supernovae and the formation of neutron stars and black holes. For now, Stevenson 2-18 continues its slow dance toward oblivion, radiating energy at hundreds of thousands of times the solar rate, pulsating and varying on timescales of months to years, and steadily losing mass to the stellar winds that will eventually consume its outer envelope. Somewhere in its core, nuclear burning proceeds toward the iron catastrophe that will end its existence as a star and transform it into something far stranger. That moment could arrive tomorrow in cosmic terms, or it could wait another few 100,000 years, but whenever it comes, it will represent one of the most powerful events in the universe, the death of a giant. The legacy of Stevenson 2-18 extends beyond its individual fate to the broader questions it raises about stellar physics and galactic chemical evolution. Every massive star that lives and dies enriches the galaxy with heavy elements, gradually transforming the composition of the interstellar medium, the oxygen we breathe, the calcium in our bones. The iron in Earth's core all came from ancient supernovae billions of years ago. Future planets forming from material enriched by Stephenson. 2-18's death will inherit its nuclear products, continuing the cycle of cosmic recycling. Studying these extreme stars also tests our theoretical understanding of physics in regimes far beyond terrestrial experience. Temperatures of billions of degrees, densities matching atomic nuclei, magnetic fields millions of times Earth's, radiation pressure strong enough to accelerate matter to escape velocity. These conditions push physics to its limits, and sometimes beyond. Each new observation provides data to test models and refine our understanding of how matter behaves under extremes. The statistical improbability of finding ourselves in the same galaxy as the largest known star reminds us that the universe contains countless wonders we have yet to discover. Every survey that pushes deeper into obscured regions or to greater distances reveals previously unknown populations of objects. Stevenson 2-18 might hold the record today, but future discoveries could reveal even larger stars hidden in distant clusters or behind dense clouds. The Milky Way alone contains hundreds of billions of stars, and we've only characterized a tiny fraction with sufficient detail to identify extreme cases. As infrared surveys improve and telescopes reach fainter limits, the population of known red supergiants will grow, potentially including objects even more extreme than Stevenson 2-18. The technological advances driving these discoveries continue accelerating as new instruments come online. The James Webb Space Telescope's infrared capabilities far exceed previous missions, allowing detailed studies of heavily obscured objects throughout the galaxy. Ground-based, extremely large telescopes now under construction will achieve unprecedented resolution and sensitivity when combined with adaptive optics that correct atmospheric turbulence. Radio telescope arrays with baselines spanning continents provide milliarc-second resolution for mass observations. Each advance opens new windows into stellar physics. The theoretical understanding of red supergiants has likewise progressed substantially over recent decades. Early stellar evolution models struggled to explain the observed population of these stars, predicting different properties than observations showed. Modern codes include more sophisticated physics, including detailed nuclear reaction networks, improved opacities accounting for molecular absorption, better treatment of convection, and rotation effects. These improvements have narrowed the gap between theory and observation, though significant uncertainties remain in mass loss prescriptions and mixing processes. Numerical simulations now allow studying processes that occur in red supergiant atmospheres with unprecedented detail. Three-dimensional magnetohydrodynamic codes can model convection, pulsations, wind launching, and episodic mass loss in ways impossible with one-dimensional models. These simulations reveal complex dynamics including giant convective cells that span appreciable fractions of the stellar radius, shock waves propagating through the atmosphere, and turbulent flows that create density and homogeneities. Comparing simulation results with observations tests whether our physical understanding correctly captures the relevant processes. Machine learning and artificial intelligence are beginning to contribute to stellar astrophysics by identifying patterns in large datasets and accelerating parameter inference. Training neural networks on synthetic spectra allows rapid determination of stellar properties from observations. Automated classification pipelines can process millions of spectra to identify rare objects like extreme red supergiants. As astronomical datasets grow exponentially with new surveys, these computational tools become essential for extracting scientific understanding from the data deluge. The search continues. If you enjoyed learning about the largest star ever discovered, make sure to hit that like button and subscribe to Space Reports for more fascinating content about the wonders of the universe. The cosmos holds countless stories waiting to be told, and we're here to bring them to you.